Up next, we've got a talk from Mohamed over from NVIDIA. Anybody who's ever been frustrated with memory safety from CUDA is in for a real treat. We're going to learn how to efficiently debug and catch those problems. And with that, I think we'll have you take it away. Go ahead, Mohamed.
Thanks a lot, Zach, for the introduction. Hello, everyone. I am Mohamed Tarek from NVIDIA. And today, I will be talking about cuCatch. As I am sure you are aware, GPUs have become increasingly popular in various applications, ranging from artificial intelligence and large language models to autonomous driving and robotics. As such, it's becoming more and more important to develop GPU tools that help developers uncover more bugs in their code. One such important category of these bugs is memory safety errors. Examples of memory safety errors include buffer overflows, where the object goes beyond their intended bound. Buffer overflows can impact adjacent objects in memory and non-adjacent ones, causing spatial memory safety violations. Another common type of memory safety errors is use after free, which typically occurs when an object is accessed beyond its lifetime. For example, here on the slide, I show a dangling pointer that can be used to access memory region after its original object has been freed or deleted, resulting in a temporal safety violation. Okay, so why should we even care about these types of bugs? Well, it turns out that both CPUs and GPUs are vulnerable to memory safety errors, and these errors are quite serious. Data about zero-day exploits that were detected in the wild over the last decade or so shows that the overwhelming majority of CPU exploits are due to memory safety bugs. When it comes to GPUs, a recent paper has showed that given a memory safety vulnerability in a deep learning framework running on a GPU, an attacker can undermine the inference results by making the deep learning predictions no longer different from random guessing. While many solutions exist for detecting memory safety errors on CPUs, the situation is quite different for GPU platforms. In fact, adapting existing CPU-based memory safety solutions to GPUs is challenging due to the various memory spaces on GPUs and its massively multi-threading nature. As a result, current GPU-based solutions are not practical. On one hand, dynamic binary instrumentation tools like NVIDIA's Compute Sanitizer require no software or hardware changes, but they do come with significant runtime overheads, and they also offer low error detection coverage. On the other end of the spectrum, hardware-accelerated solutions like GPU Shield comes with negligible slowdowns, but they cannot be deployed on existing GPUs. In order to provide developers with low overhead solutions that can run on commodity GPUs and provide high error detection coverage, we propose cuCatch. cuCatch is a software-only debugging tool that catches memory safety violations in CUDA applications. For the rest of this talk, I will first dive into the details of cuCatch, highlighting both its error detection coverage and performance benefits. And finally, I'm going to conclude with some key takeaways about our solution. Okay, so cuCatch has two main components: a novel algorithm for maintaining the memory safety metadata, which we call the shadow tagged base and bounds, or shadow TBB in short, and a novel compiler analysis for identifying the appropriate locations for retrieving the memory safety metadata, which we refer to by the base pointer analysis. The main goal of these two components is to efficiently construct fat pointers. And to be clear, by efficient here I mean eagerly retrieving the allocation base and size information without having to change the application binary interface to propagate these fat pointers through memory. Okay, so in order to better understand how cuCatch's algorithm, the shadow TPP, work in practice, let's walk through an example. On the slide right here, we have a simple CUDA program in which memory objects are allocated and freed using CUDA malloc and CUDA free, and are accessed within some while loop that runs on the device. We're also starting with a program view with just one existing object, Y, for simplicity. When CUDA malloc is invoked, a new object X will be created in memory. In this case, cuCatch is going to intercept the CUDA malloc call and store the object base and size information in a new entry within a device-side data structure, which we call the base and size table, or BST. We then take the index of this entry, let's say it is 44, and store it in the upper pointer byte, which is currently unused. This way, we can easily find the base and size information of the object pointed to by this pointer at any later time. Okay, someone might be wondering right now, what is going to happen if your ID is too large to fit in one single byte? Let's say it's 4400 instead of just 44. Here comes the shadow component of our algorithm. We use a shadow map, which is a two-level data structure, to establish a connection between an address and its corresponding BST entry. It works more or less like a page table. Some bits of the pointer are used to index into a level 1 table that holds the address of a level 2 table, which is then going to be indexed using some other bits of the pointer to retrieve the ID of the BST entries that we would like to access. In our current prototype, a 4-byte shadow map entry covers 32 bytes of virtual memory. So if the object size is, let's say, 96 bytes, it will have 3 entries in our shadow map, which we set at allocation time to the ID number, which is 4400 in our case. As a result, we are no longer limited by the number of unused upper pointer bits. In fact, we repurpose 4 bits of these bits to store a random non-zero tag that will help us catch temporal memory safety errors, as I'm going to show you in a second. Okay, now, when a pointer B that points to our object X is getting dereferenced, we need to validate its memory safety. We need to see if this access is safe or not. In order to do so, we are going to use the compiler to insert 2 new intermediate level instructions, read metadata, and safety check. These 2 instructions are going to be expanded at the compiler backend to a set of GPU native instructions in order to perform the following operations. First, read metadata simply looks up the shadow map and BST to retrieve the allocation base, size, and tag, and stores them into registers. So you can think of it as it's effectively creating a fat pointer without changing the application binary interface. On the other hand, the safety check takes the current memory address and the metadata that we have just retrieved as inputs and performs the bounds and safety and temporal safety checks. In order for us to effectively insert these 2 instructions in the correct places, we use a compile time base pointer analysis. The goal is to retrieve the metadata only once for base pointers and propagate them to all consumers. We achieve this goal by slicing backwards from memory instructions through pointer arithmetic instructions to identify the minimal set of pointers from which all other pointers are derived. Once these pointers are identified, we insert read metadata instructions for them so that we can retrieve the metadata as early as possible. And this is quite important because retrieving the metadata as early as possible offers both performance and security benefits. On one hand, it reduces the number of times in which we need to consult our metadata tables. As you see here, we only read the metadata once outside the while loop instead of doing so for each memory access within the loop. On the other hand, early accessing the metadata prevents any intermediate pointer arithmetic operations from corrupting the pointer value, which we use to index into the metadata tables. In other words, early fetching the metadata ensures that we are holding our hands on the true base and size information of the pointed to object. Finally, when this object is freed or deleted, we simply set its entries base and size to null. This way, we can effectively detect use after free errors, even if the memory is reallocated to, say, a completely different object. We can still catch those dangling pointers by simply comparing the tags from the pointer against the tag from the PST entry of the current allocation. It's worth mentioning that our cuCatch prototype handles different GPU memory regions, including global, shared, and local. We also implement multiple optimizations for reducing the number of inserted memory safety checks. Due to time limits, I am not gonna go over these details today, but I invite you all to read the full paper to know more about these topics. All right, now, as we have a good understanding of how cuCatch's algorithm work, let's go over some numbers. We implemented cuCatch in a recent fork of a production CUDA toolkit as a compiler pass for inserting these instructions and as a runtime library for managing the metadata structures. We evaluated our prototype in terms of error detection coverage, just to see how many memory safety errors we can catch with it, and in terms of performance, to understand the runtime cost of cuCatch and how it compares to other tools. To better understand the error detection coverage of cuCatch, we created a CUDA-based benchmark suite that covers different categories of memory safety vulnerabilities, as you can see in the first column. For each category, we have multiple tests that cover the subcategories. So, for example, here, our global memory tests cover out of bounds, reads and writes with adjacent and non-adjacent behaviors, targeting both device and unified memory. As you can see on the last row right here, cuCatch is able to detect over 70% of the violations versus 35% for compute sanitizer and 42% for GPU shield. Whereas 7% of the bugs result in hardware panics or the CUDA SDK otherwise detects them. The currently missing vulnerabilities include intra-allocation overflows that happen within the same object, in addition to some corner cases that are related to dynamically allocated buffers in shared memory. As for these particular cases, our back-end compiler has no real visibility into retrieving their actual base and size. Okay, so what about the performance cost of performing all of these safety checks? When it comes to performance evaluation, we compiled a wide variety of workloads with cuCatch, including kernels from various real-world applications, the Polybench suite, and most of CUDA samples SDK. We used an NVIDIA RTX 2080 Ti as our evaluation platform. However, our prototype can work on other legacy and future GPU architectures as well, because it's software only. This figure right here shows the different applications on the x-axis, whereas the y-axis shows the runtime overheads of cuCatch after being normalized to baseline execution. As you can see, most of the evaluated workloads incur negligible performance slowdowns, with the geometric mean of cuCatch being almost 19%. We can only see that we have almost 5 workloads that have larger than 2x slowdowns, which are primarily attributed to memory access latency and register spills. We have also experimented with a cuCatch configuration that only uses the shadow map. So this shadow BB only approach always indexes the shadow map every time it needs to retrieve metadata. It does not rely on the upper pointer pairs to get some sort of a shortcut on where the PST is. On average, this cuCatch configuration introduces 25% slowdowns compared to baseline, which is still comparable to our original shadow TPP approach. We have also run the same workloads using the state-of-the-art memory safety tool on GPUs, which is NVIDIA's Compute Sanitizer. And this figure right here shows cuCatch's speed-ups over Compute Sanitizer using log scale. So cuCatch is basically 1 to 3 orders of magnitude faster than Compute Sanitizer. And if you are wondering why, I would say that this speed-up is primarily attributed to the dynamic binary instrumentation approach used by Compute Sanitizer, which is way slower than the compiler-based instrumentation approach used by cuCatch. All right, so in a nutshell, cuCatch combines a novel memory safety algorithm with efficient compiler-based instrumentation to provide GPU users and developers with the debugging tools that has low runtime overheads, provides high error detection coverage, scales to arbitrary number of allocations, and requires no software or hardware changes. With that being said, thanks a lot for your attention, and I'm happy to take any questions.
Hi, this is Adam Chapala from MIT. I'm just wondering, given that there's been a lot of work on dynamic memory safety detectors for C, what were the most important differences in the CUDA setting that influenced the design of your tool, and which ideas would we want to port back to the traditional C setting?
That's a very good question. So just to make sure I understand correctly, you are asking about how the superior work in designing memory safety tools for CPUs influence our design for GPUs. The short answer is that our new memory safety algorithm is inspired by all the prior work, and it actually takes advantage of multiple prior techniques and ties them together. So basically, the idea of storing the BST entry in the upper pointer bits were proposed by a different technique, which was called GPU shield. But in this work, the number of protected allocations is going to be limited by the available number on the upper pointer bits. So we need to do some scalability. In order to get the scalability, we went to the shadow tagged base and bounds approach. The shadow-only approach have been, again, proposed before in the past as part of techniques like soft bounds and Intel NPX. But for these techniques, they require replicating the metadata multiple times in memory because they are attaching this metadata with pointer address instead of pointer value. So to avoid this cost, we use the pointer value to index into the metadata structures instead. And finally, the trick of using the 4 bits to catch temporal safety errors. This is basically was what techniques like ARM MTE is doing, but because these 4 bits only gives you probabilistic guarantees, that is not providing strong error detection coverage. So we're technically taking all of these superior work and trying to synthesizing them together to get a solution that offers all the benefits that you see right here.
Is there a reason we wouldn't want to take the same solution and bring it back to CPU applications?
Absolutely. The same algorithms that I have just just described could be applied to CPUs and GPUs as well. Yes.
Thanks.
Shripati Pai from the University of Rochester. So I had a couple of quick questions. I was curious, did you find any memory errors using your tool in these applications that you tested?
That's a good question. The question is asking about whether we have found two memory safety errors using this tool or not. I have 2 different answers to provide here. The first answer is that for uncovering memory safety bugs, we have already found a bug in the Rudenia benchmark suite, and this one is already reported before in prior work. We also found another memory safety bug in some production code that we have experimented with. Mm-hmm. And the other part of the answer is that in order to verify that the tool is actually checking or detecting all the errors we claim to cover, we created this handily written CUDA benchmark suite to verify the errors.
Awesome. So are you planning to release that benchmark suite?
Excuse me, sorry?
Are you planning to release that benchmark suite?
As per today, it is not publicly available, but we are looking into the best options to make it available to the community.
Okay, I hope you do so because, if somebody wants to improve on this technique, I see no way for somebody outside of NVIDIA to contribute anything to this, right? Your compiler is proprietary, your runtime is proprietary. So, that's not a surprise that there are no tools to do this from the community. So I hope you think very carefully about that.
These are the exact same reasons we are doing our best to make the tool and the memory safety suite available for the community. Yes,
Cool.
thank you for
you.
the suggestion.
Hi, thank you for the talk. I'm Manya from Stanford. I was hoping I could get some intuition as to why your coverage rate is higher. Presumably, if I'm just instrumenting my binary, I should be able to detect all errors. So why is your coverage rate increased? Are these other tools just not checking enough stuff? And why aren't they checking enough stuff?
So the question is about why the coverage is higher for cuCatch
Yes.
compared to different
Yes.
techniques. And the short answer is that the compiler gives us more visibility into the code, so we can perform more rigorous safety checks than other tools like NVIDIA's Compute Sanitizer with its dynamic pattern instrumentation, for instance, is unable to catch some errors that occur on the stack, or errors that correspond to non-adjacent buffer overflows when you access an object that does not belong to this pointer from another live object. Tools with dynamic pattern instrumentation does not allow you to catch these kind of errors, but the compiler instrumentation that we are using gives us better visibility into inserting this memory safety check. So this is one reason. The other reason is the algorithms that we are using, techniques like other techniques that uses tripwires, like Google's address sanitizer, for example, or ARM MTE, which uses memory coloring, has probabilistic guarantees, so it can cover certain errors or not. In our case, we are using a solid base and bounds technique so that we can catch as many memory safety errors as possible.
But you don't need the compiler to necessarily instrument the binary. Like, why is the compiler necessary? I can just take the binary. I mean, I've only done this for CPUs, but you don't need to hack the compiler to insert checks.
Yes. Okay, so why do we need the compiler? Because looking at the binary only will make us lose many information that goes from the source code to the final version of the binary. For example, when you allocate, let's say, 2 buffers on the stack, in the source code, it's quite obvious that you have 2 different allocations. But when you look in the binary, you just see one stack frame with all contiguous memory. And if one overflow happens from one frame to another, from one object to another on this stack frame, looking at the binary alone will not be enough to catch this error.
Okay,
Does that
sure,
answer your
thank you.
question? Excellent, sure.
All right, let's thank Mohamed again.